All right. I realize there is something I do need to talk about because I think it ties back to a video I already made where I said, give me a few days, I'll figure out why electrons, work the way they do. And I kind of came up with a solution, and it's just been sitting on my fridge for a week or so, maybe longer at this point. And I think it needed to sit there because it wasn't fully fleshed out, but I think I have seen some other stuff and tied it in, and I've kind of made some connections here. And I know that this is probably not going to be well received because it once again it requires relating the super large to the very small, and I don't think people like that. They don't think they're the same thing. But here I am going to try and show you that maybe they are, or at least they behave the same at the very least, right? Um, and this started with, okay, we have an atom, right? And in the atom, there's the nucleus, and then there's electrons flying around, right? And initially, we're shown the orbitals, and it's like, oh, the electron orbits around the nucleus. That's what we're taught. But then, if you go into quantum stuff, then you find out, oh, well, actually, or if you go just a little bit farther in, I guess, science or chemistry, you find out, well, it's really not orbitals like that. It's more like clouds, right? We've got these electron clouds around, and we don't know exactly where the electron is in this cloud. We don't know exactly how it moves around in this cloud, but we know it's in this cloud, right? There's a high probability it's in this cloud. And so we have these clouds set up everywhere, but we don't have a defined motion anymore, technically, for these electrons. They just have a cloud of probability of where they're at, right? And so, pretty much, my theory here is kind of goes back to the reason why, the orbital theory got thrown out is because they were like, well, why doesn't it fall into the nucleus, right? It should fall into the nucleus, but it doesn't do that. So, what gives? And, a question I could ask is, why doesn't the Earth fall into the sun, right? Hello, Future Sam here. I'm going to pause it and kind of go over what I was trying to say here because my description was decidedly terrible, and I felt like I had to re-explain why the electron getting smaller allows it to move away, and when it gets larger, it gets pulled back. And it has to do with gravity, as I was saying. But the reason why, I don't know if I really made it clear enough, is when the mass of the electron, sorry if I misspoke earlier, but the mass of the electron, when it's smaller, is, as I've discussed in another talk, is more attracted towards smaller particles, right? The smaller particles' gravity will cause it to be pulled towards them more than it would if it had a larger mass. And so when this happens, there is actually, in the direction towards the nucleus, there is less energy there. So there is less pulling it in that direction. And there is more in the direction away from the nucleus. There's more to pull it away from the nucleus than there is to pull it towards, because the nucleus is pulling in the energy. And so what happens is that because there's more energy in that direction, that's the direction it gets pulled, because it is more impacted by local gravity rather than the larger gravity of the nucleus when it's smaller. And as it does that, it gets accelerated because the farther away it gets, the more there is out there to pull it in that direction. But as it gets pulled out, it's also starting to also gain some of that mass because it's getting some of that, the mass that it's getting pulled towards is also being pulled towards it. And so as it moves, that mass is starting to accumulate. And so that's why it starts to accelerate out towards the outer edge of the nucleus. And as it heads out, it's building that mass up. And as it gets to a certain point, though, which is what I called critical mass, is it gains so much mass that it is no longer capable of being pulled farther from the nucleus, because it's gotten to a point where its mass is large enough that it's more impacted by the quote-unquote global gravity, which would be the nucleus in this case, compared to the local gravity, which is all the virtual particles that are around the electron, right? So the critical mass point is that point where it no longer is being pulled, and instead it is starting to pull everything towards it. And at this point now, it has a problem, right? Because as all it's doing is pulling things towards it at this point. And at this point, it just keeps building and building and building. It's pulling more and pulling more and pulling more in, right? But there's that point where it no longer is moving away at all. And at that point, its direction becomes pulled back towards the nucleus, because now the only thing with a larger mass than it in its vicinity is the nucleus. And so it starts to get pulled back towards the nucleus because everything else gets pulled towards it instead of pulling it away. And so it starts to get pulled back towards the nucleus. And it's at this point that the electron is now heading back towards the nucleus, and it's heading back towards less and less energy. And so because of this, it's burning energy to sustain its mass faster than it's getting it returned back to it. And so it causes this massive decay, spontaneous decay, as everything that it got pulled towards it and basically assimilated into its overall energy is now got to get dumped out, because it can no longer there's no longer enough energy to keep them bound to it. Right now the energy within the electron is less than the energy outside of the electron, and so everything will fly out basically and go towards where there's more energy. And so that is why we get this spontaneous decay and this emission of a photon. And as this happens, then it's already getting pulled back towards the nucleus at this point, right? But there's also, because of this big emission that happened, all of the energy in the general vicinity has been excised as well, right? So there's nothing to stop it from falling back towards the nucleus. And so it continues to fall back down, and then it doesn't start to build up its mass again until it's gotten closer to the nucleus and outside of that zone of its quote-unquote, photon emission or, energy ejection event. And so I feel like I kind of missed that explanation and tying that into some of my previous talks. So I just wanted to kind of add that in right here. So, yeah. I wrote down here, its critical mass is reached. And at this point, it can't gain any more mass, and it's pretty much that point where I feel like I'm not explaining this well, but trust me, it makes sense. I swear. When you throw a ball up in the air, the point right here at the top, right before it starts falling down again, that is basically critical mass. It's flying up, and then for a brief instant, it basically stops. It pauses, right? And then, boom, it falls back down again. That point where it pauses, it's very brief. It doesn't just chill there and do nothing necessarily. It's very brief, right? But it stops, and then that's when it reaches its critical mass, right? And when it stops, when it stops moving, it's no longer able to take more energy in and becomes unstable, right? And this is effectively what absolute zero would be. And that's why it's really hard to get absolute zero. And my theory is that if you did get something to absolute zero, it would just decay, right? And then I came across this and I was like, you know what, this actually makes sense with that because, when we think about a star, right, and a star's life cycle, right, it grows, it burns through its energy, it, potentially takes in more energy in, right, it burns through all of its energy, and then it'll basically go boom, right? And then release just a ton of energy all at once, right? And we know that electrons will get excited, right, to a high energy state and then release a photon, right? And then they fall back down to a less energetic state, right? Well, pretty much what I'm thinking here is, what if a gamma ray burst or a supernova is effectively a photon being released by an electron, right? And then it falls back down to a lower energy state. And that's basically what we're observing. What if every single photon is a supernova going off? Wouldn't that, isn't that insane? Or a gamma ray burst? We think these gamma ray bursts are so powerful. Imagine living in the universe of this room with all this light in here. No wonder why life is so hard to exist, because what are the odds you're dodging all of these gamma ray bursts, right? We're getting pretty lucky, I would say. Anyway, moving on. And so it releases it, right? And then it releases all that energy, and because of that, it gets pulled back towards it's allowed to move again, and it gets pulled back towards the nucleus. And so it falls back down to the nucleus, and then comes back to that orbital equilibrium point, misses the nucleus, right, and then goes off again and gets launched back out, and kind of repeats the whole process over again, right? And the reason why we have these orbital clouds and we have these high probabilities of where we will find the electron is because a majority of the electron's time is spent in between its critical mass and its equilibrium point. It's only in those two spots very briefly, right? The majority of the time is in between those 2 points. And the only time we can actually observe it is when it's releasing energy at its critical mass point, right? So we get this orbital that we think is this energy level here, right? But that's actually just its maximum energy. That's the maximum energy it can have, right? And we know that if you excite an electron past this maximum energy, then it is shot out of the nucleus, right? And that's called ionization. You've ionized that nucleus because you kicked the electrons out, right? And that is effectively just like you gave the electron enough energy or enough velocity basically to achieve escape velocity and break out of the nucleus's orbit, right? Or gravitational pull. And without you adding that energy in, there's this, like the Earth is not going to break out of the sun's orbit without adding energy into the system, right? It's just gonna kind of chill here. It's stuck, right? And I think electrons are a similar thing. And basically, I wrote out these energy circle things, and if you have one axis, right? Pretty much I have one axis. We're drawing like a circle, right? On a polar coordinate. We're drawing a polar coordinate circle basically. And we have basically real and imaginary. It can almost be kind of seen as, because we have the mass axis, which is real, right? And then we have the velocity axis, which is the imaginary, right? And this is referring to the imaginary energy compared to the real energy, right? Because something that has something that is pure mass, right, has no movement and is not that's not like a it's going to decay, and because that would be effectively absolute zero. If it's pure mass, it has zero velocity, it has zero motion. That's absolute zero. That's not a stable thing, and whatever that is going to decay. In order to reduce the amount of energy necessary inside that circle will then, when it decays, that circle will then, kind of collapse and reshape itself so that its mass to velocity is balanced again, or something along those lines, in the conditions it's within, right? So, if you put something really dense, like you put a dense atom or a heavy, like a large atom inside absolute zero, it's going to go, uh-oh, and it's going to pop into something smaller, and then that's going to go, uh-oh, pop into something smaller, or it'll just instantly pop into something smaller. I really don't, small enough. It'll either kind of go through stages of decaying, keep realizing that it's not cold enough, it's still too cold, or it will just instantly go from one to whatever is, survivable. I don't know. Hard to test something that we haven't been able to achieve yet, right? So, speed of causality is when you have only velocity, right? So imagine something has no mass and only velocity. Well, that would be pure energy, right? It would basically be the speed of causality. That's what the speed of causality is something that has no mass and has just pure velocity, right? And we say, oh, that's the speed of light, and light has no mass, but I'm telling you it's wrong. That's not true. I'm telling you that's a bunch of baloney. Light has mass. The speed of causality is the speed of causality. It is pure velocity. And so, to us, that's kind of imaginary because, in theory, we can't do that, right? We can't be basically pure energy. We can't be outside of time because, time is energy basically for us. So to be outside of our energy source and still surviving and thriving, it's not really something I could suggest. I don't know how we would go about it at this point in time, but it's also the imaginary because the mass of an object is, its rest energy. The rest energy is E equals mc squared, which is based off of the speed of causality and mass, right? But then, so that is like a definitive, no matter how fast you're moving, the mass of that object is going to be consistent. Its rest energy is going to be consistent. However, it's I call it the imaginary because it's relative energy, right? Because it really depends on how fast you're moving is what decides how much energy the other object has, right? So if you have two objects moving at 200 miles an hour, effectively there is no energy between these two objects because they're moving at the same speed. They might as well be not moving at all, right? But if one of them is moving 100 miles an hour and the other one's moving 200 miles an hour, now there's energy there. Now there's an energy difference, right? And now it's basically like one is moving at 100 miles an hour and the other one's still, right? So the energy in that system is relative, right? This 200 mile an hour object only has energy to something that's not moving 200 miles an hour, right? And so it's really kind of an imaginary energy. It's not the same. It won't be equal for every observer. And because of that, I'm considering it the imaginary axis because it's relative, relativity. And that is defined by the part of the momentum part of that equation, basically mv squared, right? Causality is a given. Everything moves at the speed of causality because causality is how everything moves in general, right? You don't need to specify the speed of causality plus velocity because it's implied, right? Everything moves at the speed of causality, and regardless of your current velocity, everything moves at the speed of causality, right? Like, as Einstein says, right, like the speed of light is constant regardless of how fast you're moving, right? But really that's not true. That's the speed of causality that's true for. And so we can, and I can prove that that's not true by redshift and blue shift. If the speed of light was constant, right, regardless of your speed, then blue shift and red shift would not exist. And you can't tell me different because that doesn't make any sense. The difference in energy is entirely dependent on how fast you're moving. And therefore it is not constant. Anyway, speed of causality. Right? The speed of causality is constant, and in theory. And so, you only really need to, when you're trying to find out what the relative energy of two objects are, you don't need to worry about the rest mass, really. What is more important is its relative energy, which is mass times its velocity, and its velocity could be the speed of causality, or the speed of light or whatever, but in comparison to you, right? But most likely a lot of objects, it's not that fast, right? But, imagine two particles flying at almost the speed of light, right? The difference in velocity for them is not going to be still the speed of light. It's going to be a smaller value. Probably might still be a lot, but it's going to be a smaller value than the full value of the speed of light. And I want to just do a quick side tangent and apologize, because I do recall basically taking a big fat dump on the whole momentum part of the equation. But in my defense, for what I was trying to say, I was totally in the right, and I'm not wrong for saying what I said. But the momentum is relevant. It just wasn't relevant for what I was trying to say at that time. And I realize now that it wasn't a bunch of, pointless numbers on the board there. It does make sense, and it helps a lot when you're trying to describe an electron and why the electrons would behave in this manner, and how that all works out, because like I said, there's that relative energy, and it's defined by just whatever that velocity of the electron is and what its mass is, right? And so depending on what its mass and velocity is when it enters, it changes how it behaves within the system. And so electrons are in an orbital cycle that is created through a relation of rest and relative energy, and their release of a photon is similar to a supernova/gamma ray burst, as afterwards they reduce in energy and fall back to orbit where energy is regained. Maybe I put here like a pulsar is akin to a neutrino with periodic cycles, and we think that the mass of a neutrino is increasing and decreasing, but maybe it's just that, like, how like a pulsar kind of like points in a certain direction and it spins around. Like, what if like we're experiencing the energy beam and we're seeing that as high mass, right? Because mass and energy are similar, right? And then at certain times we observe it and it's like over here, right? And so it seems like we're not getting the full beam anymore, right? And then it moves over here and it's really tiny. We're not getting much of the beam at all at that point. And then it just kind of keeps going around in cycles, and it's just kind of doing something like that. I don't know. It was just a thought, right? I put it here. I'm not super confident in it, but I accidentally started reading it, so I figured I would finish saying it. Anyway, yeah, so I'll show my drawing that I have here because I was just talking through it, but here's my drawing that I got going here. So there's that. And the reason why I got these circles going is because I was watching this video. I watched this video, just kind of like a random thing that popped up about it takes like a pi amount of collisions for like a block of a given mass to be like reflected back, or it's like it gets closer and closer to pi the more the larger the mass difference is. And in their explanation, basically, in order to get the block to completely turn around and move in the opposite direction, you have to completely 180 its momentum, right? And in order to 180 its momentum, well, what is that? You have to turn a full pi. Like 180 is equivalent to pi. And so this collision number is equivalent to a ratio of, okay, every time this block hits this block and then this block hits the wall, each time there's a collision, there's a certain ratio of energy being dissipated, right? And you need to dissipate that amount of, like, the same amount of energy, whether there's a block there or not. Because imagine there's no block, the larger block hits the wall and bounces off in one thing. Well, that is equivalent to still pi, right? Like that the energy that was needed to do that, right, is still equivalent to pi, is still equivalent to a 180. And so when you put something in between them, it has to then transfer that same amount of energy, and it can only do it in certain like chunks, because every time it hits, right, energy is sent from this into the smaller mass. But the larger this mass is, the less energy can be transferred into this each time, right? Because as soon as it gets hit, it gets, its maximum amount of energy basically. It goes bink, and then it goes bink, 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 right? And you get this like circle. And in their description in the video, they drew out this circle, and I was like, okay, this energy circle idea, I really like this energy circle idea. And so I drew it out, and I put like, okay, well, on this side it's the mass and the velocity, and I was like, wait a minute, this makes like a lot of sense. And then I was like, well, what will happen if it's pure mass, right? Because I was thinking about balanced energy states, and I was like, okay, well, it makes sense that a balanced energy state would be like a perfectly round circle, and then the circumference of the circle would be this, like, the perimeter or circumference of the circle, whether it got stretched in one direction or the other, would be constant, but the values can change, right? So you can have less velocity but more mass and still have the same amount of energy, but you could also have less mass but more velocity and still have the same amount of energy, right? And if you want to make more energy, right, the only thing that you can do is, like I would say that the volume, or not the volume, the area of the circle is like that total energy, right? And in order to expand that, you've got to expand your circumference, and things along those lines. And I don't know, I just really liked the idea of it. It just made so much sense. And so I drew it here, and I don't know, I just really like it. I think that it's at the very least very good for intuitively understanding, visually understanding what it is I'm trying to say when I say pure velocity or pure mass, and why it causes that to be the case. But basically, E equals mc squared is rest energy. E equals mv squared is relative energy. E equals rest plus relative energy is, I'm going to call the momentary energy, because at every given moment that value is changing, because the velocity is either changing or the mass is changing, and at every given instance, it's unlikely that the energy in a system has stayed completely constant. And so I put momentary energy because it's the energy at that given moment, and is not necessarily the same at every given moment. So, the E equals mv squared comes from just momentum times velocity, momentum times velocity, and momentum is just mass times velocity. So mass times velocity, v squared. So rest energy is dependent on causality, and so it is the defining factor for balanced states of a system. Relative energy is the difference in energy between two objects relative to each other. Momentary energy. All right, I don't know, apparently it cut off, so I'm going to just read again what I just said because I've been talking too long. So E equals mc squared is rest energy, E equals mv squared is relative energy, E equals rest plus relative energy is momentary energy. Rest energy is dependent on causality, and so is the defining factor for balanced states of a system. Relative energy is the difference in energy between two objects relative to each other. Momentary energy is the energy At a given moment in time, as the energy of a system is constantly changing, velocity is the controlling factor in momentary energy, as its value is squared. This is why something with less mass but has a higher velocity has more useful energy. And what I mean by that is like if you have a big rock, right, that's not moving, there's basically no energy there, right? But if you have a little ball, right, that is flying at, 100 miles an hour, that's got a lot of energy, right? Because velocity determines energy a lot more effectively because the value of velocity in the energy equation is squared, right? So, if you have your mass equal to 5, right, and then your velocity is equal to 5, well, your velocity is now 25 compared to your mass that is 5, right? So a larger increasing the velocity increases the energy a lot faster than increasing the mass does. And so it's a lot easier to put energy into something that has less mass than something that has a lot of mass because, effectively you're trying to, change that velocity value in order to get its mass, in order to get its energy up. And it's just easier to do that when there's less mass there. To, kind of because when you're pushing on an object that has a lot of mass, it has a lot of energy, right? In order to, and what's happening is when you're pushing on that, the energy that is being, the force you're feeling, like the pushback against you, and the fact that it's not moving is that energy being realized, right? Because that equal and opposite reaction that is talked about, right? The equal and opposite reaction, that is energy. There is energy there. The energy you're pushing in is getting pushed back at you, right? Because that's how, large masses work. That energy of, pushing back against you is the energy that is inherent in that massive object. But all of its energy is in its mass, right? And if you start getting it moving, it's got a lot of energy, right? So you imagine like a wrecking ball, right? That's what it's called. A wrecking ball, right? If you try and push on a wrecking ball that's on the ground, it pushes against you, right? There's a decent amount of energy there, but it's not anything too crazy, right? It's not gonna knock a wall over by just you putting it next to the wall, right? But now if you put it on a chain and you drop the wrecking ball and it goes poof into the wall, well, all of a sudden it's got a lot of energy, right? I don't know if I'm just totally off on a rant here or if that was a necessary explanation for you to understand what I'm talking about, but there it is. So, basically this initially started with me talking about why electrons do what they do, but it kind of devolved into why energy is what it is. So, I don't know, I guess we hit 2 birds with 1 stone, maybe, I don't know, maybe we hit neither. We threw 2 stones, but we missed both birds. Who's to say? We tried. There's always tomorrow. Anyway, that's that. I don't know. I thought the drawing was pretty good. I don't know. I feel like it explains what I'm trying to say pretty well. So, I don't know. Between this drawing, my drawing talking about why particles move towards higher energy rather than lower energy, and then my one talking about what magnetism and what the magnetic field and electric field are down at their particle level. Those three in combination, I feel like, are really all you need to understand what it is I'm trying to say here. Basically, what I'm getting at, the full scope of everything is the only defining force, the only fundamental force is entropy, and gravity is basically entropy incarnate. It's how we can visualize entropy taking place, and it is the defining characteristic of every interaction. You go, oh, why is this happening? Oh, it's gravity. At the bare bones, it's gravity. And gravity is just the movement of energy towards energy. And the reason why it moves towards energy is because energy is being consumed. And so as energy is consumed and entropy is increased, and balance and flow is all being enacted, we get this. I don't know. It's absolutely insane. I don't know, because I was thinking about it and I was like, we could, if my theory holds true, we are basically, our entire universe, potentially, our solar system at the very least, is within an atom. And then that atom might be within another atom, and that atom in another. And we are just literally nothing. We're literally nothing in nowhere. And it's like that concept is so insane, because it's like, no, but we are something. We're real. Like, we're huge compared to something, but we are nothing compared to something else. And it is just so weird to think that. And I don't know what to do with it, because at the end of the day, I still got to wake up in the morning and go to work. So it's like, I don't know. It really comes back to my, before I started getting into physics and thinking about this stuff, I was really interested in like philosophy and stuff like that. And one of my favorite quotes or I don't know if it's like a quote or if it's like a special passage or something, but it's before enlightenment, chop wood, carry water. After enlightenment, chop wood and carry water. And just something about it, like when you get to that point and you're just like, that's beautiful. That is beautiful, because it's true. Because it doesn't matter if you find out all the answers to the universe, because you're still in it. You still have to live here. You still have to do stuff. Like, it doesn't change anything. And so, like, if my realization is right, and like basically we're nothing, right? What does it change? It doesn't change anything. It'd be like, wow. Anyway, right? Like, it doesn't matter, but like, it's just so crazy, right? Like, I don't know. Yeah. I don't know. Anyway. Peace out.